of our unit packet. There are a couple of questions on your mid-unit test aligned with what we're going to learn about today. So you want to make sure you are paying careful attention to what you hear about so that you can apply this tonight. There's an explore activity up here at the top that I want to begin with before we anchor ourselves in much more concrete information. This is designed to get your brain thinking in a different way than it has been thinking with our previous lessons. Bless you. You know me. As soon as you start feeling okay with something, that's a cue for me to shift gears and introduce something new, right? And y'all are doing better with your unit circle, so now we're going to train our brains to approach problems in a different way as well. So my hope is that you can look at these 4 questions that are on the top of page 33 and collaboratively try to come up with some answers to these. I'm going to give you some insight first before I give you a space to try and just uncover what's going on here. When I look at number 1, the question asks us to solve for any angles that satisfy these equations. This first equation is sine of theta equals 1/2. We have done questions like this in the past early on in the unit where we had a calculator at our disposal. Do you guys remember what button on our calculator would cancel with the sign right here? The sign inverse, right? With the little -1 up at the top. That's how I would solve this in the past when I had a calculator. I don't have a calculator today, but I have my circle, and that's gold, right? Literally gold, because it's on yellow paper. No? Anyway, that's going to be the primary tool we use to hopefully address this question. Before I just give you freedom to try to figure this out without me, let me pose the question to you that I ask myself when I see something like this. I generally pause and I internalize what angle, and I'm actually going to put that little S in parentheses because it could be more than one, has a sine of 1/2. This is the question that I ask myself when I see an equation like this. I'm going to put 2 minutes on my timer, and I want you and your table mates to not only try and answer this question that I've posed on number 1, but push yourself to see if you can come up with answers on 2, 3, and 4 as well. Use your circle, use your definitions up there, and see if you can put these pieces together. 2 minutes, go.
Oh, wait a minute.
Thank you.
Wait, no.
For the sun, we have to look at the y.
Yeah.
So that could be
So we're done.
y over 6.
Do we have to?
Y over 6. Can you be negative?
Yes, about it.
What about the negative?
Nope.
If it's asking for
Oh, you're
more,
right.
hi everybody.
Somewhere.
For the sign, we ask for the y.
There's your best friend, Harold. I thought he took going.
What?
You know,
You're right, aside from piracy. Because I got one other one.
Okay. Y over 6 is 5 pi over 6.
It's different than what we have. Same thing.
Nice. All the people I've seen put that in ratings. Try these ones too.
For culture, X.
Wait, I just realized the pattern.
Oh, sorry.
That's whack. What? Woman?
All right, here's what I'm seeing on many papers. When posed with this question, what angle or angles has a sine of 1/2? Many of you are arriving at a conclusion of 30 degrees and 150 degrees. Can I get nods or snaps if that's what you came up with? I'd like to shout out Vanessa because she pushed herself even further, and this is something I didn't even have to encourage her to do. She did it on her own. She gave me answers that I like even more. Can anybody predict what I'm about to write? Pi over 6 and 5 pi over 6. Your brains are still in degree mode because that's what's comfortable for you, because that's how you've always measured angles in the past. My brain's comfortable in radian mode because I've had to do this now for many, 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 many moons. Your brain needs to start really acclimating itself to radian notation because that's the form all of your exams are going to be in for the most part. So, great job, Vanessa, with pi over 6 and 5 pi over 6. Knowing that, would anybody like to share out potential answers for number 2? Push yourselves. 7 pi over 4 is an excellent answer. In degrees, that's 315. That's his equivalent for the radian counterpart. Any other answers? Selena? Beautiful. 5 pi over 4 as well. That's 225, our radian counterpart. Fabulous. And it's the same question we posed, right? What angle has a sine of negative square root of 2 over 2? Beautiful. That circle helps a lot in these kinds of questions. We run into trouble on number 3, though. The question is, what angle has a cosine of 3? Cosine is x or y according to my definitions up there. X. And if I scan my circle, is there ever an x value that is equal to 3? I look, I see square root of 3 over 2. I see 1 in a couple of places, but never do I find a location where the x value is 3. That simply means that the answer to this question does not exist. There is no angle where I have a cosine of 3. Good job. Not true here, though. I can find a place where cosine is -1. Claudia, where is that place? Pi. Very nice. Oh, both Claudias in unison. That was impressive. Pi. Or 180 degrees if your mind is still in degree mode. Pi. All right. What is true that is kind of frustrating, but nobody picked up on it yet, so I'm going to share with you something. Do you remember what a coterminal angle is?
No.
Can someone be brave and share with us what coterminal angles were, Angela?
It's an angle and like the same on the opposite side it has the same thing.
What do you mean?
Like it's the same placement on the circle, but just on the opposite side.
Okay, so she's saying same location on my circle. Give me more.
It's the angle that you need to reach the horizontal.
Careful, you're talking referencing right now. Give us just a little bit more, Genesis, on coterminal.
Is that one where you like when you rotate it negative 270 degrees and then you could have gone the other way and made it easier?
Okay, so y'all are both communicating exactly what they are. Give more, yeah.
And so then what I noticed was that those angles are coterminal angles of each other. Or like
Not
based on the same-
necessarily. They're a little bit opposite. Yeah, go for it.
Different values that end in the same place.
Okay, different angle rotations that end in the same place. Okay, that was our definition of coterminal angles. This question that I posed, what angle has a sine of 1/2? We gave 2 answers here. I would argue there are actually an infinite number of answers to that question when I consider coterminal angles. Pi over 6 are 30 degrees, right? That's one place. But if I added 360 to 30 degrees, I'd get another place where I still have a sine of 1/2. I could add 360 again, as many times as I want, and I'm still finding solutions to this question. The way to account for that, which is annoying, you're not going to like it, but it's a blast from the past, is to take these answers of pi over 6 and 5 pi over 6, bless you,
Thank you.
and add 2 pi n to those answers. to indicate that I can continue adding full rotations as many times as I want and still maintain the accuracy of that equation. That's annoying, I know. And because of the fact, that there are actually infinitely many solutions to these equations, what we're going to do in this lesson is restrict the window with which we look at when we solve equations like this so that we don't have an infinite number of answers. All right? We're going to be talking about domain restrictions and range restrictions and inverse functions and all this good stuff today. Go to page 34 for me and we can start this conversation. You guys don't know how lucky you are that your second period, my poor first period, my guinea pigs, I know I've told you this before. I try so hard to share things with them and I fail miserably every day in first period. But then I'm great for you because I know what doesn't work and I like try and approach it differently. But we're going to talk about sine right now and inverse sine, okay? We've had many conversations in here about inverse functions. Been a while, but we did that in Unit 1. We also did it in Unit 3 when we learned about logs and exponentials, inverse relationships. We're going to try to gain a little bit more structure with our inverse trig functions that we're going to be using for the rest of this unit. Good news, maybe. There are 6 trig functions, yes? And when you hit that trig button on your calculator, there are actually 6 inverse trig functions as well. We are only going to work with the first 3, inverse sine, inverse cosine, and inverse tangent. We will not use the other 3 in this course. So, we have had absolutely no exposure so far in this course to the graphs of sine, cosine, and tangent. However, here's a nice preview of what the graph of sine looks like. I think this is just a beautiful curve right here. Goes on forever in this same motion. We call this oscillating behavior, continues bouncing up and down in oscillating form. What is true about the sine function is that this function would fail miserably what we know as the horizontal line test. Agree? If I put a horizontal line on this graph, I would cross so many times, infinitely many if I looked at the whole curve. Which means when we talked about horizontal line tests in the past, if a function fails the horizontal line test, that means its inverse is not a function. Which means these inverse buttons we're using would not be functions if we looked at this entire curve from negative infinity to infinity. In order to address that, what we're going to do is restrict the domain of the original function, which in turn restricts the domain of the inverse function. And the range, actually. It restricts both. But by doing that, I'm going to really zoom in on a chunk of this original graph that would pass the horizontal line test, resulting in an inverse that is a function. That's the whole thing. I want to work with functions only in this class. In order to maintain that, I have to chop off the ends of the sine curve and only look right here in the middle. By doing that, the inverse graph, remember, the domain of the regular original function becomes the range of the inverse function. The range of the original becomes the domain of the inverse. Everything just flips. So what this means is that now moving forward, when I use inverse sine, I'm not going to have infinitely many solutions like what we saw in that original activity. Because the inverse sine function is only going to exist in this small window right here. Because of that, the answers I produce when I use inverse sine have to be from negative pi over 2 to positive pi over 2. We're going to restrict our range or our possible outputs right now to maintain that function characteristic when we look at these operations. Unfortunately, the restriction is not the same for cosine. It is the same for sine and tangent, negative pi over 2 to positive pi over 2. For cosine, however, we have to restrict from 0 to pi. What I've done to make life easy today is I've recorded those restrictions up here at the top of the board, and I put them in degrees because I think that's more natural for our brain at this stage in our lives. Degrees. we're gonna use that to help us address some upcoming questions. I talked about this for like 15 minutes in first period, and they were looking at me kind of like some of you are, like, huh, what's she talking about? And then we started doing some, and they were like, that's it? Why didn't you just say that? I said, I'm sorry, I have a history of like talking things to death, and I apologize. I will do better in the future. I did a little bit better with you, but I feel like I'm still talking you to death, and I'm sorry about that. Here's what I want you to do. On your yellow piece of paper that's become like the keeper of all the important things this unit, can you please write those red restrictions on there as well? If you're feeling fancy and you want to put them in radians, please do. If it's easier for your brain to work in degrees, which I think is probably the majority of you, let's write them in degrees for right now. I have you till 45. So once you get those recorded, we're going to try some model problems here to really hone in on this inverse trig idea, which is totally different than what we've been doing in the past, but really aligned to that explore idea or a couple problems that you just did. When in doubt, this key concept box on the bottom of page 34 summarizes all of this info. So you can come back here and dig in more detail. Another sort of unfortunate thing is that our inverse trig functions, which I've written up here in one form with that -1 notation, can actually be expressed in a different way too, and you need to have exposure to both. Sine inverse of an angle means the exact same thing as arc sine of an angle. Well, not of an angle, my bad, just of x. What you need to know is that these mean the exact same thing. So when we see the inverse notation versus the arc notation, same idea. For both scenarios, your goal is to find an angle as your answer, like we did on the previous activity. Arc is another way to represent an angle on our circle, an arc that's formed. That's the only difference here, but they mean the same thing. Here I go again, talking things to death. Can we do an example? I need to be quiet. Yeah? Carol's like, yes. 35. Okay, so here's the goal. When we see something like the first problem on 35, notice arc sine is the notation that's used right here. If that's tricky for you, that is absolutely the same thing as sine inverse of 1/2. Those notations are interchangeable. When it's an inverse sine or an arc sine that you're presented with, the goal is just like it was on the Explorer. The question you ask yourself is, what angle has a sine of 1/2? We go to our circle, we try to find the appropriate angle whose sine is 1/2. If I break this down even more, I pause and I remind myself, well, sine is y. So I'm going around and looking to see if there's a y value of 1/2 anywhere. Now, if I just inspect my circle, I find 2 spots where that happens. This is aligned to the first problem we did earlier. I think it's 30 and 150, right? Now, though, the extra piece I need to consider is that my answers have to fall in this window. And only one of those locations is between -90 and 90. 150 is outside of this range. So I get to throw that one out the window, which means the only answer to this question is 30 degrees. Or you know me, I would much rather prefer to see that as pi over 6. Done. This is when they were like, man, miss, why didn't you just say that? It's not as bad as you made it out to be. Okay, good, I was glad. Let's try this. Gotta be between -90 and 90. Here I'm looking for a sine of 1. So let's look at our circle. Is there anywhere where the y value is 1 as I scan my circle? Harold, where?
Pi over 2
Good, he gave the answer in radians. He said pi over 2.
minus.
Many of you might need to chunk that in a slower step, right? By 90 degrees first, and then write that as pi over 2. Is that in my window? Sure. That's why my answer is 90 or pi over 2, and I quit. One thing to note, these are brackets, so we can include 90 and negative 90 in our answers, right? That's why that is okay. Sine inverse of negative 2 pi is the next one. This means I float around my circle and I try to find a y value of negative 2 pi. As I look at my coordinate points, and you should be familiar enough with these now to recognize, nowhere on the outside of the circle is there a y value of negative 2 pi. Nowhere. What do you think that means my answer is right here?
Does not exist.
Does not exist. All right. I want you to try the next 4, and please ground yourself in these restrictions that we created. You should expect a little bit of healthy struggle when you get to those tangent questions. Those are good. I believe you guys can put your brains together and try and sort this out together. Let's take 4 minutes. That should be plenty of time. Really think critically about those tangents. Those are good ones. What? There is. That takes some getting used to because you're used to looking at the whole circle. But for cosine, I actually only know the
Maybe because it's tomorrow. It doesn't matter. How can I say?
I don't want to see that, but I don't know. It could be wrong. I don't know that either.
This one is
Between 90, negative 30, 90.
does not
No,
exist.
it would.
And
All
this
right.
one,
I'm going to give answers to the first two because I think those are a little more straightforward. answer for arc cosine is 3 pi over 4. Or if you're still in a degree mentality, 135 degrees. One thing to note, when I look at the entire circle, I also consider 225, or 5 pi over 4. That's another place where cosine's negative square root of 2 over 2. However, my restriction throws that one out the window, because I have to only live between 0 and 180 for cosine. Okay? Cosine inverse of 2 does not exist. I don't care where I look, I'm never going to find an x value of 2 on that circle. Absolutely. And then we get to these, which are much more rigorous. With arc sine and arc cosine, I like those because I'm just scanning the x's or scanning the y's. Tangent, however, is tricky because I have to be thinking about the ratio of my y to my x. And this takes some getting used to. I am trying to locate a place on my circle where I can divide the y-coordinate by the x-coordinate and get -1. I'm also trying to do that in this limited window from -90 to 90. And one thing that's interesting, your unit circle that we worked so hard to create yesterday only contains positive angle measurements, right? We never went in a negative direction when we labeled our circle. So I have to think really critically about what this -90 means to me right now. If I start at 0, 90, that's easy. I go up to the y-axis. -90, I go down to the negative y-axis. So it might say 270 on your circle, but a coterminal angle to that is -90 degrees. So here's what's interesting. When I'm dealing with inverse sine and inverse tangent, it's simply quadrants 1 and 4 that are relevant to me. Those are the ones that meet this restriction up here. If I want to try to find a tangent of -1, think about this. One of these quadrants is much more relevant to me because of the negative sign on that tangent expression. Which one, Kimberly? 4. In quadrant 1, what's true about quadrant 1? All positive. That can't get me that answer. So I know I'm looking in quadrant 4. And because y'all are getting so much stronger at this, I believe many of you can look in quadrant 4 and realize it's going to be that 45-degree angle down there, not the 30 or the 60. To get a 1, regardless of if that's negative or positive, I'm going to need to be dividing two things that are identical to one another so that they cancel themselves out. And it's the 45-degree angle where I have square root of 2 over 2, negative square root of 2 over 2. Those two values, when stacked on top of each other, will do a nice cancellation and be left with a negative sign, or a -1. Now, be careful, because on your circle, this angle looks like 315, because we rotated in a positive direction on our yellow papers. What is the equivalent coterminal angle if I rotate down?
45.
Negative 45 degrees. That's the answer here. Or again, if you're feeling extra fancy, negative pi over 4. Awesome. With that same mentality, we've got about 2 minutes to try and get some insight into the last one. Still looking for a y over x, but that ratio needs to simplify down this time to square root of 3. That's what I'm looking for. Quadrant 1 or quadrant 4, where should I focus my energy? 1, where things are positive. And based on what we saw down here, when I look in quadrant 1, I'm actually not concerned with the 45-degree angle. I already know when I divide the y by the x, I'm going to get 1 at 45. It's really going to be either the 30 or the 60 where this happens. The point at 30 degrees is root 3 over 2, 1/2. Up here it's flipped, 1/2 square root of 3 over 2. The answer here is 60 degrees, or pi over 3. And the work that I'll do to show you that, to confirm that conclusion, is to look at the 60-degree point, take square root of 3 over 2, the y value, and divide by the x value, 1/2. How do I simplify this fraction division?
KCF.
KCF, good. I keep square root of 3 over 2. Change the division to multiplication and flip that thing over. What happens, what do I notice on top and bottom? The 2's, yeah? Out of here. When I simplify, I'm left with square root of 3. That was what I was trying to find. So 60 degrees, or pi over 3, is the angle that makes that ratio. There's one more slight variety that we'll talk about tomorrow in the context of the model problems down below, and then we're going to start rotating a little bit differently around our circle and getting a feel of some more interesting questions. That's it from me. Do your mid-unit test tonight. Did I finish? Wait.
Meeting with 45.
Yes. Hi, Emily. Crazy. Okay. Good. I'm so sorry. I thought we looked at 40. I'm getting myself mixed up with third. Okay. Good. I want to model then the other kind of application you'll see with inverse trig. It's weird. I'm going to preface it by saying it's weird. If you look at this next model problem on the bottom of 35, you will notice there's a composition here. A much larger expression that we're going to try to solve. Cosine of tangent inverse of negative 3/4. When I did this with first period, they remembered back from algebra that when I see complex expressions like this, I should start on the inside and work my way out. Do you agree with that sentiment? Work your way out, kind of like unpack the expression. So when I look at this, I'm starting then with the tangent inverse of negative 3/4. And to anchor myself in my thinking, I'm trying to answer this question. What angle has a tangent of negative 3/4? That's the question I'm trying to answer right now when I tackle that interior expression. I'm remembering that tangent limits me to quadrant 1 and quadrant 4. And based on what I saw in those previous two examples, I don't believe that any of these significant angles is going to generate a ratio of 3/4. Those numbers aren't relevant to the points that we've created for ourselves on our circle. Here's what happens when I attempt questions like this. My go-to is my unit circle, and I try my best to find an angle that meets this expression using my circle. Many times, though, my circle is not helpful, like here, and I strike out when I look at my circle. If that happens, my next best strategy is not a circle, but instead a triangle. And I'm going to try to anchor myself in a triangle and get myself some support in that way. So here's what I mean by that. When I see that the tangent is negative, can we all get on board that it's quadrant 4 that's more significant than quadrant 1?
Okay.
All right, so I'm going to come over here and really hone in on quadrant 4, and I'm going to draw a right triangle. Based on my definitions over there, tangent is the ratio y over x, yes? So this is kind of spiraling in an old skill. What I see here is that the y value of my right triangle is negative 3, according to that given info. And the x value is 4. Is it possible to find the hypotenuse of this triangle?
Yes.
We've been doing this a lot. Does anybody just remember what goes with 3 and 4?
2. 5.
5. Yeah, it's a 3, 4, 5. Good. We could do Pythagorean theorem if we weren't sure, but it's 5. So check this out. I have a base angle here of theta. I don't know the number of that rotation, but that's my angle, and I've created a triangle that has a tangent of negative 3/4. Yes? This angle measurement meets that interior criteria. When the question says what angle has a tangent of negative 3/4, this one does, right? I have found an angle that has a tangent of negative 3/4. I have answered that interior question by way of this picture. Now all I need to do is find the cosine of that angle. This becomes an old school problem now from the very beginning of our unit. you guys from geometry all told me many times that cosine is the same as adjacent over hypotenuse, right? Do I have an adjacent and a hypotenuse? Sure. I tried to train your brains to think of it as an x over an r, but an x and a radius, same thing. My final answer here is just form fits. A very different strategy for handling these inverse trig functions, but a helpful one. Hint, hint, hint. Hint, hint.
Hi, Emily.
Bye,
There's your friend
Emily.
Harold.
Everybody say bye, Emily.
There's your friend Harold here.